Hello and welcome back to Real Analysis. And first I want to thank all the nice people that support this channel on Steady or PayPal. In today's part 27 we will finally talk about continuity. Since we've already discussed it in the last video, we can immediately start with the definition here. So what we need here is a function f with domain I, where I can be any subset of the real numbers. And now this function is called continuous at a given point x0 if first the limit of the function f as x tends to x0 exists, and secondly it should be the same as f of x0. Here it's important to remember that this is indeed a local property. This means that if you have a graph like this, you would fix a point x0 and you would zoom in at this point and look what happens. Also, you already know in the definition of the limit we have two directions. So what happens when we come from the left hand side and what happens when we come from the right hand side. And when both approximations go through the value at this point, we say that the function is continuous at this point. So for this definition it only matters what the function does around this point. And for this reason we have to talk about a special case that can occur. Of course, it can happen that the domain I is not an interval. This means there could be some holes in the domain of definition. Therefore, for example, at this point we only would have the right limit. Which is of course not a problem because the whole limit still exists. It just gets simpler because we only have to look at one direction. However, what happens when this direction also does not exist? In this case, the limit symbol here does not make any sense. Hence, for such an isolated point in the domain I, we need another definition. Now here please recall, continuity should exclude jumps we could have in the graph. And of course, for such an isolated point here, a jump in the y direction cannot happen. Or in other words, when you zoom in at this point, there is nothing around. Or to put it in other words, if you zoom in at this point, you see there's nothing around this point. Therefore, for such points, we also call the function f continuous at this point. Here, isolated in I just means you don't find a sequence xn from the outside such that the limit of the sequence is x0. However, still the important case is that we have a point that is not isolated such that we need this condition here. And with this we have the whole definition for f being continuous at a given point x0. And now we can simply extend this definition to all points in the domain I. This is a common procedure to make a local property global. Now a given function f is simply called continuous, or if you want to emphasize the domain you would say continuous on I, if f is continuous at all points in the domain I. So the property from above holds no matter which x0 you choose. Therefore, an important thing to remember is that continuity helps you when you deal with sequences. Roughly this means if you have such a limit, you can pull the limit symbol inside the function. Of course, you also have to put in that this limit exists and lies in the domain of f. However, in this case, the continuity of the function f tells you that this operation here is allowed. Okay, with this I think we are ready to talk about examples. Let's immediately start with a simple one. If we have a constant function, then no matter what the domain is, it's always a continuous function. This is not hard to see because the sequence of the values is always a constant sequence. Now, if we manipulate this example a little bit, we get a function that is not continuous. So here we have two constant functions that we put together, which tells us that we here have a jump at 0, because the left limit is different from the right limit. Therefore the function is not continuous at the point 0. The problem is simply that the limit at this point does not exist. However, at any other point we don't have this problem. Hence we have continuity everywhere else except at 0. Okay, next let's look at a similar example. Here we just change the value 0 at one point. And we already know this from the last video. Therefore we already know the result here, it's not continuous at the point 0. You already see the jump here. However, now the limit exists at this point, but it's not the same as the value at the point 0. But still the result is it's not continuous at the point 0, but everywhere else. Okay, let's also recall a positive example from the last video. This is just a general polynomial which can be defined on the whole real number line. And it can be written in this form where we have coefficients ak. And now you know we have already showed by using the limit theorems for sequences that we have continuity at all points. Or more explicitly, we have shown that the limit x to x0 is the same as f of x0. Therefore, such a polynomial never has jumps. So this is a very nice and important example of a continuous function. A straightforward generalization of such a polynomial is a so-called rational function. And it is also a continuous function everywhere where we usually define it. The definition is simply given by a fraction where we have one polynomial in the numerator and another one in the denominator. And for this reason, in the domain of definition, we have to exclude the points where q of x is 0. However, then we get out a nice continuous function. Indeed, it's not hard to show the equality here, we just have to use the limit theorems again. Because we have one limit theorem for sequences that considers a quotient. Okay, maybe at this point it might be helpful to look at a very concrete example. What we can do is to look at the function given by the absolute value. So we know by definition the absolute value is given by two cases. For positive numbers we don't change anything, and for negative numbers we change the sign. And of course 0 stays at 0. Therefore the graph of the function looks like this. So you see, for every point except 0, continuity is clear, because there it's simply a polynomial. There we just have to consider minus x, or in other cases on the right hand side just x. However, for the point 0 we have to consider both cases at the same time. Therefore let's calculate the limits. First let's consider the left limit when we come from the left hand side. So we consider a sequence xn that is always less than 0. Therefore we are always in this first case, so we can substitute f of x with minus x. And then this limit is easy to calculate, it's just 0. Then in the next step, of course, the right limit has a similar calculation. There we can substitute f of xn with just xn. Both times we get 0, therefore the limit exists with value 0, which is the same as f at the point 0. Therefore the result is the absolute value is a continuous function. Okay, now for the last example we should choose one that is not continuous. It's also easy to define, but what we get is that we don't find any point where the function is continuous. So we put the function to 1 when x is a rational number, and otherwise we put it to 0. So what you should immediately see is there are a lot of jumps involved. Now an important fact we can use here is that q is dense in the real number line. And this is indeed what we have by construction of the real numbers. However, of course, the only thing we need is the meaning of this. It tells us that every real number can be approximated by a sequence of rational numbers. So for any real number, you can take a sequence of rational numbers where the limit is this real number. And indeed, the same works with sequences with irrational numbers. And exactly for this reason, this limit here does not exist. Simply because you can take a sequence that stays at 1 the whole time, and you can take another sequence that stays at 0 the whole time. Therefore we can always produce two different limits here. So here we have an example that is at no point continuous. Or you could say it's everywhere discontinuous. So please keep that in mind. Continuity is a special property and not all functions have it. Okay, then in the next video I will talk about the epsilon-delta criterion for continuity. It's important because some people use it for the definition. Therefore, I hope I see you there and have a nice day. Bye!